In example 4, we have a gas that expands 1.2 liters at a constant pressure of 2.5 to the power of 5 pascals. During the expansion, 500 joules of heat is added, and we're asked to find the change in internal energy of the gas and draw a PV diagram with our solution. So let's start with the first part here of doing the PV diagram part. We know that this is a constant pressure process. That means it's isobaric. An isobaric or constant pressure process, that would be shown in this PV diagram as a horizontal line, because on the y-axis we have pressure and that's remaining constant. So and we also know that it's expanding, so it must be moving to the right because we're increasing in volume. So we'll start off here with this initial point. We'll call that A, and then we're going to be going to this final point B, and it's moving at a constant pressure process and an increase in volume. You can see I put a little arrow to show the direction of this process. Let's label some of the things that we know. We know that it has a pressure of 2.5 to the power of 5 pascals. That's given. And we know that we don't know the initial end volume. All we know is really the change in volume is 1.2 liters. Okay. We are also told the 500 joules of heat is added, so let's just put that over here. Q is 500 joules, and it's going to be positive because it's added. Now we're asked to find the internal energy change, which is equal to, by the first law of thermodynamics, the amount of heat added or subtracted plus the work done by the gas. At this point we know the heat, but we don't know the work done. How do you think we're going to find the work done? Hopefully remember that work done is the area under the PV curve. It's negative area under the PV curve. So it would be equal to, since the pressure is constant, really just negative pressure times the change in volume. So that would be 2.5 times 10 to the power of 5 pascals multiplied by the volume, which is 1.2 liters. But you may notice that these things are not in the appropriate units. See, a pascal is really Newton per meter squared, but the volume in liters is not right. We really want to put those units into liters, changing to meters cubed. Hopefully you recall that 1 liter is equivalent to 1,000 milliliters, and a milliliter is the same thing as a centimeter cubed, so that's equivalent to 1,000 centimeters cubed. And since in 1 meter we have 100 centimeters, or in 1 meter cubed we have 100 times 100 times 100 centimeters cubed, then we'll find that this really is equivalent to 1,000 divided by 1,000,000, which is really 1 to the power of -3 meters cubed. So 1.2 liters is really 1.2 times 10 to the power of -3 meters cubed. And that will give you an answer of the work being equal to -300 joules. So now we're ready to plug this into our first law of thermodynamics. Our change in internal energy will be equal to the heat, which is 500 joules flowing in, minus the work done, which is 300 joules. So it's really plus the work done, but the work done is negative. And that will give you an answer of 200 joules of internal energy change. So although there was some negative work being done as the gas expanded, doing work on the environment, there was more heat that flowed in, and hence the internal energy change was larger and it went up. So only a certain portion of the heat that flowed into the gas was used to do work. And that's it for this example.